Okay, let's move. I thought I understood move semantics when I last Christmas started to write a little bit about it, and I learned that I did not. And so this is a talk where I try to tell you a little bit about this whole thing. And this is not a talk with slides. This is a talk about implementing a simple class to store email addresses, actually a single email address. And of course, this class should have good performance. And therefore, move semantics is something we are interested in. So let me start with a class. I have a class here. This is my email class. Let's go through it step by step. Class email. Okay. Oops. Okay. Class email. So what's an email? An email has a string value and a state. And the state could be none, an email value is set, or the email address was even validated. So we know it's a proper email address, whatever that means. So let's try to initialize the email address, having a default constructor. We have here an initial value none, and here this string is empty, so that's the initial state. And then we have the ability to take a string, initialize a value with the string, and check the state. The check state function is a helper function that will evaluate this email address and find out whether it's empty, so whether it's none, or whether it's set, or whether it's even valid. So for the moment, we don't want to look any more against that. Here we just find an ampersand. So if it contains an ampersand, it's valid. And of course, a lot of other things are missing there. And then we have a getter returning the email address. So get value, returning this by value. We will talk about that. And finally, we have an output operator. The output operator just will print none or the email address in angel brackets, or if it is a valid email address.
Hey, Nico.
Okay, behind. Yeah.
The audience is asking if you could make the font of your text and your code bigger, that they can better follow along.
Okay, so let's do that. That or even big.
I think a bit more, yes. Just make it really big.
So that.
Okay, thank you.
Oh, my screen is not big enough. Okay, let's see. So, good. So, class email, a value and a state, constructors, we can check the state, getter, and we have an output. That's all. Looks like a pretty forward class. Let's use it. So let's use it in some test code. Yeah, I will change the font here also. So let's use it here. Let's create a vector of emails with some initial emails, my email addresses, and an empty string, and an invalid email address, so having no ampersand. Anything else? Yes. Let's push some additional email addresses there. We have here from the command line from argv, argc, argv, we get a default value of 10,000, 100,000. And 100,000 email addresses we push in there, but we can try out different things. Print out the email addresses with a helper function that simply iterates over them and prints the first four and the last four of them, so we don't print the whole collection. And then that's all. Simply sort the email addresses here, go from begin to end, And our sorting criterion is, yeah, we sort according to the value of an email address. So that's straightforward code, I think. No surprises should be here, I hope, at least. Let's compile it and run it. So I will also change the size here. Okay. So let's compile and run it. To compile it, I have a couple of compilers available. Let's start with the C++14 compiler. And so you see it's GCC 5.5 with -02, and a couple of warnings are enabled. And let's run it. So here you see the initialization takes 220 milliseconds, and the sorting takes about 4.5 seconds. On this platform, that's not a proof, just to have some numbers. And you see that here we have the elements. The first ones I initialized here are these 4. And then we have the other 100,000 email addresses. And then we have here them sorted. So empty email addresses first, and then there comes the others. And you see that when I print it out, every email address that is valid has an OK after the email address. Good. That's it. Can we improve the speed in this simple class? Yes, we talk about move semantics, and we can improve one thing here. So the first thing we can improve is this constructor. This constructor takes a const string reference and then uses this to initialize the string member. Well, that's a problem, because you might have already a string value you no longer need, and you might want to move it to this member. But this doesn't work because you take the argument by const reference. So what could we do instead? Well, so let me comment out the old thing we did, and let's switch to a new thing. Let's take the string by value and move this value into the member. So the constructor takes the argument by value, which if you learn C++ might be something you learned as a surprise. No, don't pass a string by value. But this time, this is something different, because we anyway have to create a new string as part of a new email address. But when we take the argument as a non-const string value, we can benefit from move semantics. So let's take whatever we got. Maybe it's just created here on the fly. Maybe it's a copy, or maybe it's a move. And then move this here to the string value. Remember that if you take a const string reference, you could not move it to here, because for const objects, its move is not working. So let's recompile. And let's run again. Yeah, you see. This is a significant improvement. So initialization now takes less than half. Yeah, don't take these numbers too serious. It's the only thing that this shows is there's a remarkable improvement. The improvement depends on the amount of optimization you use, the platform you use, the way the standard library is implemented. So whatever you use here, there might be some chance for improvement, and you see it might be significant. Are there other ways to do that? Of course, you could overload for different cases, for taking a non-const R-value reference and a const L-value reference. And so you could overload for different cases. But here we have a simple way to do it. This works and has good performance in all cases if, and only if, a move is cheap. Because we have a string here, and there move is cheap. If this value member would be an array of 1 million doubles, this might be counterproductive. So be careful with this improvement. This is not always an improvement, but in many cases, it might be. Okay, that's the first thing we can benefit from move semantics. So what else can we improve here? Look at the sort function. The sort function takes around between 4 and 5 seconds. So can we improve that? And yes, you might see that we use or might remember that as a sorting criterion, that's here, we call getValue. So each time we have to compare two values, two email addresses, we call getValue for these two email addresses. And that's called a lot when the sorting algorithm is called. And each time this count getValue member function returns a new string because it returns a value by value. So that's the old flame war or discussion we have in many projects. Should a getter return by value or should it return by reference? And there would be significant improvement if we return by reference. So let me again uncomment this and instead return the value by reference. So let's recompile and see how the numbers are. And run. Ooh, that's huge. That's huge. Sorting got faster by a factor of 10, about 10. And it's clear, I mean, we save a lot of time where we create a new string intentionally. By the way, my strings I use have significant length. You see here some of them, so that the short string optimization is not used. But even with the small string optimization, there might be some significant improvements. It depends again from platform to platform. But of course, if we save to copy a string, especially if the string needs memory, that goes faster, significantly faster. So we should return by const reference. Wait a minute. Let me go to this program and add a new line. And in this line, I want to iterate over the characters of a temporary email address. That's my favorite example when I discuss with people, should a getter return by const reference? So for each character C in just a new temporary email address, this is a function I use, next email. So next email will give me the next email address. And then in this email address, I would like to have the value and iterate over these characters and print them out. So let's print out C, maybe a space, and at the end, let's print new line. Let's run. Email test. Oops. So it compiled, and let's run it. Yeah, looks good. Works. Let's compile it with another compiler. Maybe we use Visual Studio, so Visual C++. So let's use that. and run it again. You see here something interesting. You see here nothing. So it seems the iteration over the characters of the value of a new email address is not printed. And the reason is, first of all, a problem we have in the range-based for loop, which I really hope will be fixed very soon. I am just proposing a paper for that. And the problem is that there's some hidden mechanism behind the scenes when using a range-based for loop, and these mechanisms extend some but not all lifetimes. So it's not like a function call. It's more like that this value has a lifetime, and that lifetime gets expanded throughout this loop. But while the loop internally runs in a range-based for loop, the lifetime of the return value here is not extended. So we iterate over a destroyed email address. And what you see here is a result. Whether it works or not depends on the platform, depends on, I don't know, your memory use, etc. So you might get a call dump, you might get undefined, you have undefined behavior. And part of undefined behavior is that it might simply work as it did here. And that's my favorite example, that returning a reference is might be a problem, because this means you refer to a member of an object and you have to make sure that the object is still alive when you then use the return value, which is a problem in the range-based for loop. But you can easily create this situation in other cases. So now we have a trade-off. Should we be safe and slow, or should we be fast? Well, there's a new option introduced with Move Semantics. And this option looks as follows. We can do both. We can overload functions. You know that. You know that probably that you say, oh, let's overload functions for a const and a non-const version. These are just a way to say, well, let's like overloading for different parameters that are qualified differently. Now let's qualify the object we call this member function for differently. But I don't overload for non-const and const. I overload for temporary objects and other objects. So the one thing I say is there is a special implementation for temporary objects. Well, in fact, this is for our value references. So our value references bind to temporary objects or PR values, and they bind to objects marked with move. So for these objects, I have here an implementation. And as this is for temporary objects, especially, so they might die as here in the for loop, but as I told you, this is not the only example. Let's change this and say, well, let's return it by value. And for everything else, and const reference, we have here an implementation for all others. So this binds to all, but this has higher priority for temporaries, so this is preferred for temporaries. So now we have a fast getter, and we have a safe way to deal with, to ask for the value of an object that's about to die. And yeah, let's compile and run. And this was, by the way, introduced with C++ 11, also with Move Semantics. And you can and should use it if you return expensive things, expensive members from your object. So email test now also works in Visual C++. Good. Because we fixed our bug, it was very okay that Visual C++ worked the way it did. Actually, it was good. We saw a problem. And it also works now with GCC. And we have pretty good performance. You see here the sort function. We have a fast sort function because the getter here, we call it for objects that have a name. So we use this getter only if we have a temporary object, like here, we use this scatter. Okay. So that was the second thing. Let's add another thing. Let's in our program add remove from our container all values that have .com in it. So Timo just mentioned remove if, and he just learned that there's a caveat with remove if, and that's caveat I want to use also in this talk, interestingly. So let's go over our collection. And remove all the elements where we have where we find .com. So we return if em.find em.getValue.find .com is not equal STD string n plus. So our remove criterion is if we find a value with .com, we remove it, which is almost all elements in this program. And then let's print it out. Okay. Oh, no error. That happens rarely when I do a demo coding. Email test. So here you see something interesting. And it's funny, really funny that Timo just uses remove if in the talk before. Because he told you already that remove if works the way that it changes the order of the elements. It can't remove an element in a container because it only deals with iterators or pointers to the container. So it can only modify values of the elements, but not remove elements from the container. And so actually what does remove if do? It moves all elements to the front that have not .com. Well, actually, these are only these three elements. These are moved to the front, and everything else, and everything else is either untouched, or we move the old values there away. And as you see, before we remove the elements, these are the three last elements, or these are the four last elements, and now we have them here because this value and this value was moved to the front. And now you get an interesting effect, because you see that now in the container we have an email object that has no value but is classified as being valid. Okay, so what happened? We move this value to somewhere else, to here. So we use move semantics. And the way the move semantics is implemented, that it moves the members. So we have a value and a state member. So we move the value, yeah, the value from here moves to here. So we'll use the value here. Oh, excuse me, talk about this. This value is moved here. And look at the last element. The value from here is also moved to here. So we lose the value here. The output of a move for strings is a valid string. You don't know the value. It might not be empty. It could have any other value, but it's very typical. And in all implementations, the fact that the value is moved in a way that the moved from object, the object that had the value and where the value was moved away, is empty. So we see that here. But we also move the state. Well, the state is just an enum. There's nothing with move semantics to optimize. So we copy the state, and that's the effect. We copy away the state, we move away the value, and at the end, we have this value. Now you can discuss about this a lot, because you might say, wait a minute, that's okay. I mean, the last element in my collection is no longer valid. It's not a valid email address. And that's okay, because you have moved it away. But to some extent, we usually expect that if objects have invariants, so if objects have certain states, consistent states, that we don't create objects that have an inconsistent state. You might argue, well, it's your problem if you use the last element. But at least in the standard library, we guarantee that moved from objects are always in a valid state, so in a consistent state. And that's for a good reason, because if they are not in a valid state, operations might no longer work, up even to the destructor. So the question is this a problem or not? And please also know that you didn't call move. The move was called inside an algorithm, and there might be functions that do it that way. And yes, we should not use the removed elements anymore. By the way, when you compile that with the Windows compiler, it gives you a message that you should not use, that you should use the return value of remove if. This is in German, but it tells you because then that's a new end, that's a new logical end. And with that help, you might better see that there's a problem. The question is, how safe, how good, how sane would we want to have this email class to be? So should we allow that move semantics creates inconsistent states? It's your issue whether you think it's an invalid state or not. Or should we fix that? If this, at least if this class is used in a lot of places, it's probably better to fix that. And so let's look how fix would look like. Again, I don't say you have to fix that, but you might create interesting situations if you have a class that looks like it does guarantee, gives you an invariant, a guarantee about all the objects that exist, which state they have, and this is suddenly broken. So let's implement it. Let's fix this. And how can we fix it? Well, there are a couple of options you could try out. So the first options may be that you say, oh, let's disable move semantic. Okay, and maybe the naive approach is we disable the move constructor, and we disable the move assignment operator. Maybe I switch back to the QCC compiler, because then I have colored output. So you see, it seems to be run in a little problem. So what is the problem? If you declare move operators as deleted, there's a rule that you have also deleted the copy operations. So no move, no copy is possible anymore. So we have also to enable, to explicitly then enable the copy operations. So const email ampersand and const email ampersand here, and let's set this to default. Still a problem. Why that? Because here's an interesting other rule. If you mark something as deleted, you say any try to call this is an error. So if overload resolution finds this, and it says, delete, it says, oh, it's not allowed to call this. That's different from not being declared, not being there. Not being there means if overload resolution doesn't find it, it might take a fallback. And in fact, if move semantic is requested and it's not supported, the copy operations are used. But here you say, no, forget with the fallback mechanism. Only allow copying, not allow moving, which makes no sense at all, by the way. So it's the correct way to disable move semantics is to default other special member functions, for example, the copy operations. And now we have it, and it compiles. Of course, we don't benefit from move semantics anymore, and we will have it will take longer here. It's about double the speed here, and yeah. So, and by the way, this is interestingly, this is a violation of the rule of 5. You might have learned that either you declare one of the 5 special member functions or none. Excuse me, either all or none. This is not right when you want to disable move semantics, because there is no way to declare move as please don't find it. So delete would be wrong, default would be wrong. You could implement it, but that would really be crazy. So in this case, the rule of 5 means if you declare or implement one of these 5 special member functions, think about the others, but not necessarily declare it. Also a consequence of move semantics. So, well, we have a little bit worse of performance. So the other option would be to implement these 2 functions. And that might, in this case, definitely be the better option. So let's implement it. And let me write this here. So the values of a new email address is initialized with the values of an email address, but we want to move them. So std move. And we also do the same with the state, but state has no move semantics. So we take e.state. And for that, so far, that's what the usual move constructor would do. But we do something else. We give moved from objects a guaranteed value. And for that case, we say e.values clear. Let's make sure this is an empty string where we got from. And let's especially set the state to state none. That's correct. That this is state none. Yeah. Okay. Oh, and more or less the same we have to do in the assignment operator. So here we need assignments. So e.values equals the moved values from here. Sorry. The new values are the moved values from here. And oh God, it's on video how bad I type. So, and the state is state. Semicolon. Here the A is wrong. Let's compile. Let's see. And we should here say this. Oh yeah, value. Oh, that's interesting. Oh, first of all, here we need this. And oh, what did I do here? This is, I have to implement these, the move operations. Yeah, I'm sure you saw that already. So, and there must be parentheses. It's getting better. I still get an error because, of course, now I implemented the move operations. And once we declare them, and that's the case when we implement them, we have disabled copying. So we have move-only types now, but we still want to support copying. So that's also enabled copying. Now it works, finally. Good. Yeah, and speed is better. Again, we don't have an inconsistent state here. You see the moved from object here, which was this one, is now a valid email address. Good. Look at the number of initialization. Can we improve that a little bit? Yes, because if you implement move operations, you should tell whether your implementation throws an exception or not, or could throw an exception or not. The reason is that the vector uses, when it uses pushback, uses move semantics if it has a guarantee that there will be no exception, because pushback has a rollback guarantee, and if we move values away, we can't roll back. So if you move a couple of values and then you got an exception, you have a problem with this guarantee. We gave this guarantee in C++ 98. So this was a problem we found very late in the standardization of C++ 11. And at the end, we introduced a new keyword called noExcept. And with this keyword, we can say, okay, by the way, I guarantee that this will not throw. And there are some discussions and some ways you have to do that. And you can say, even conditionally, I give this guarantee if my members give this guarantee, etc. But in principle, this changes the performance again. So look at the numbers now. And now we have here 200 milliseconds, and before we had 250. That's not 10 times faster, but it's significant. And the reason is that now when the vector grows and grows and grows, reallocation now uses these move operations instead of using copy operations. Good. And the good news is, if you just declared with equals default your move operator, the compiler will fill out no except for you. So this is only a problem if, in case you have to implement a move operator, which should still be very rare, but you have seen here one example, especially if two members and the state of two members depends on each other. Okay, we are almost done with a significantly improved class email. If you think about the starting class we had and how simple it is, just two members here. But there's one more thing, and then there's one more thing. And that's it. Look at here, the print statements. These print statements I have used here is that I use a helper function that takes begin and end. And as you can see here in the output, it will find out whether this, what we print there, is a non-const or a const vector. So we call print, and we could call it for a const vector. So const std vector of email back. And that's called here also call begin and end vec dot begin, vec dot end. Well, it's empty, but I just want to show you that the print function here makes a difference. And because yeah, you see here we also see that we pass a const vector, but here we see we pass a non-const vector, but here at the end now we can't pass a const vector. So why am I telling you that? Because I want to do some improvement. I want to make some improvement. I want to say, let's provide a helper print. This helper print takes a collection. Well, we can take a collection of any type, template, type name P, and we take this collection yeah, as a const reference. And what we internally do is pretty simple. Let's call print with collection.begin and print with collection.end. So I think you see the point. So let's take an arbitrary collection and call another print that takes two iterators, begin and end. So does it work? Well, we should test it. So after this, two prints, I should also call this new print. So let's do it right behind. Let's print the collection, and let's print the vector. You might see already the problem. And the reason I teach you that, or tell you that. And as you see now, here, these are the last two containers, a non-const vector and a const vector. And now we have only a const vector. So that is clear because when we pass a container to this print, we make whatever we get const, because it's a const reference. Okay, so let's take a non-const reference. So this declaration would make everything const. Oh, let's not do that. Of course, I should comment this out. So. And it works. Good. So let's print it. Oh yeah, great. Non-const, const. So that's a good thing of template type deduction. Here we get T gets a type of what we pass. If it's a const vector, T is a const vector type. If it's a non-const vector, it's a non-const vector type. So great, everything is fine. Well, is it? Well, let me do something different. Let me call print with a temporary vector. So std vector of email initialized with nothing. Okay. So, and here you see problem. Invalid initialization of a non-const reference from an R value of type so-and-so. And the problem is, this is a temporary object. This is not an L value, an object with a name. This is a temporary object. And non-const references can't bind to temporary objects, so to PR values. That's a value category. So this doesn't work for PR values, temporary objects. So what is the solution? Well, we have something new in C++ 11 with new semantics. We have something that is sometimes called universal reference, sometimes called R value and forwarding reference. So the universal or forwarding reference. I still think universal reference, that was the initial name introduced by Scott Myers, is a better term because it can universally refer to everything. Well, not to everything, not to, I don't know, functions or so. But it can universally refer to all expressions, L values and R values. So if I do it that way, and you see it compiles, and it keeps the information whether the containers were const or non-const. And that's a good thing. The reason I wanted to point that last is I'm not very happy that this is called the forwarding references, because as you see, we don't use it for forwarding. Well, to some extent, you can say we forward some information, but which, by the way, every reference does. But calling std forward here would really make no sense. You could only call it once, saying I no longer need this. So you could do something like this and say std forward of T of call, and for this object we use begin, but saying for two objects I no longer need the value looks a little bit weird, because forward means I no longer need the value semantically, like move means that. And if you pass it with two arguments, does not really make sense to do that. And it's not necessary, as you saw. Maybe I leave it in and uncomment it. So here I wanted to motivate a little bit that we also need universal or forwarding references somewhere else. And if you don't use templates, of course, now with new C++ versions, you can use auto here instead. So you could use, since C++ 20, auto double ampersand here, since C++ 20, and that should work. And that's my final version. And let's compile it with a C++ 20 compiler, and you see it works, again, the same way. That's it. That's not all about move semantics. That's all I wanted to tell you about that in just some live demo. So let's see what we had. We had, for expensive members, initialization might better take by value and move. For getters, there you might overload for R-value references and const L-value references to once return by value, once return by reference. Moved from objects are nothing special. Functions, algorithms use them just as other objects. So we have seen that in remove if. And you might at least think about not breaking invariants, so guaranteeing that even a moved from object is an invalid but unspecified state. In my new book, I discuss a lot about this in detail. In many cases, it's okay as it works because rarely people use a moved from object, but just to be safe, you might think about that. To disable move semantics, don't delete a move special function. And in fact, deleting a move special member function is never useful as far as I know. And by the way, this breaks the naive understanding of the rule of 5. And use no except when implemented special movement functions. And there are universal or forwarding references which might not forward. Well, that's why I still name them universal references. It's a little bit pity that the standard committee introduced a second term, although we had one in the C++ community. But that's a different issue. That's it. We are right on time. You will find this code probably a little bit better because I did it with more time before the talk at my website, josuttis.com. Download meeting CPP. And you find the first version and the last version with some comments. And of course, I should point out that I learned all this by writing this book about move semantics. It's done now, and it has 260 pages. And you saw some significant parts of it. If you want to have more, yeah.
So there's 2 questions. I'm going to paste them in the...
Oh, yeah.
Yes. Mahmoud asks, in get value &&, shouldn't you use constant &&? The problem is the same for constant temporaries, isn't it?
So you mean here? Here?
I suppose so.
Well, no, don't use a reference to something you return here, because that's the implementation for a temporary object that's about to die, and you're running exactly the same problem. It doesn't matter whether you return a reference with a single ampersand, so an L-value reference or an R-value reference, the problem would be the same. By the way, I see here something. I missed something. When we return here by value, we can here return with std moved because the temporary object no longer needs the value. I forgot that. And that will even improve the performance of the program we had. And another question?
Yes. The other question is Friedemann Client asking, would the speedup be similar if the constructor was spelled out in a CPP file and not inline? This was like very at the beginning of the talk.
Here, you mean when we switch from here to there, would we have the same speedup or not?
Yes.
It depends so much on a lot of things. If it's not inline, that's an issue. I saw if you move and you don't optimize with -02 using CPP, using GCC, etc., the performance might get worse. And we have different performance on different platforms. So this is a signal, I would say, because conceptually we have to do 2 memory allocations if we just have this constructor. This is better. And if you know that memory allocations might happen, and for everything else, please measure. Again, it's a little bit tricky in C++ to come up with general rules. It all depends.
There's one last question from Sasha, and it is about, I noted that there is std move if no except, however, there is no std forward if no except. Do you know some reasoning behind this? No,
I don't know that. The move if no except was proposed by people who implement the move semantics in, for example, things like in vector, where they say, if this was passed with move semantics, then we use a move, otherwise we do a copy, and maybe they didn't use it for forward. And even move and forward are not enough for all situations. I just wanted to implement, for example, perfect returning and deferred perfect returning, deferred to later. And there, neither move nor forward could work. You had to implement yourself what forward does. So I think it's just a workaround that came from implementers of library. Usually, it might help, but if not, implement yourself a significant similar helper function.
Okay.
Good. If that's it, thank you very much. Well,
I think we have time for one more question. So there's a question about what about RVO? I meant returning std move value that you presented answering the first question. Okay, so I read that again. What about RVO? I mean returning std move value that you presented answer. Okay, so you returned their std move for value. And what about RVO in that case? Wouldn't RVO be better?
Well, this is not RVO. This is not a local object that's created inside this function. It's also not named RVO. This is nothing like that because we have no local object. This is an object which is a member of the object we call this function for. That's outside the local scope of this function. So the rules of RVO and NRVO do not apply here at all.
Okay. Thank you for your talk.
Thank you very much, guys. Take care.